All right, section 17.6 is more about the acidity of carboxylic acids. So why are carboxylic acids called carboxylic acids? And that's because they are the most acidic group of all of the functional groups in organic chemistry, meaning that um, that they have pretty low pHs. All right, so carboxylic acids react with a base to be water soluble. If you remember from Gen Chem days, um, if you react an acid with a base, you get a neutralization reaction. And that's kind of what we're doing here. If you take a base and react it with the carboxylic acid, the proton that's attached to the oxygen is the acidic proton. All right, so what happens is this hydroxide grabs the hydrogen to form a water molecule. So notice this right here forms water. All right, and you get a negative charge. The electrons right here between your oxygen and hydrogen go on the oxygen to give you a negative charge. And the sodium is the counterion. It's kind of like a double replacement reaction. If you remember the double replacement reactions, this part joins up with this part, all right, and then this hydrogen pairs up with the OH to form water. And you always form water and a salt. Okay, so the carboxylic acid, it donates a proton to the base, which accepts it. Okay, um, it's what's called a carboxylate anion. Okay, and they're called salts of carboxylic acids because it's technically a salt. Remember, salt is anything that has a metal attached to a non-metal. Okay, so that part of it is the non-metal. All right, salts of carboxylic acids formed by acid-base reactions are water soluble. So octanoic acid is not water soluble. The way we know is because it has more than the 4 carbons. Okay, so this is not water soluble. However, when you treat it with base and you deprotonate it and you now form an ionic bond, we know ionic bonds are very soluble in water. So because we form something that's ionic, it is now very water soluble because it's ionic. Okay, so the reaction will turn a water insoluble carboxylic acid into a water soluble carboxylic acid because it's now ionic. Okay, so in the organic form, it's insoluble. In the ionic form, it's water soluble. And we actually saw this when we did the solubility lab. We had a carboxylic acid, I believe it was octanoic acid, and it was not soluble in water, but as soon as you got base to it, it does become soluble. Okay. This is just kind of some naming, just to kind of give you an idea. This isn't something you're going to have to do on the exam, but if you ever see these names, it's the name of the metal, followed by the parent, and then ending in 8. All right. So, for example, the name of this is sodium acetate. This is an acetate ion. Okay. Potassium propanate. Okay. So those would be the names of those: potassium propanate, sodium acetate. Okay, an interesting carboxylic acid, or things you do with carboxylic acids, especially long carboxylic acids, is you make soap out of them. This is how you make soap. If any of you have ever made soap before, you basically take lard or you take oil, which is some sort of triglyceride, and you add lye to it or base to it, and it turns it into soap. Okay, soap has very interesting properties. We're actually going to talk about the chemistry of soap. Okay, soaps are basically the salts of carboxylic acids. They have many carbon atoms, long hydrocarbon tails. Okay, and the soap is actually in 2 parts. It's has a nonpolar tail with a polar head to it. Okay, so a polar ionic end and a very nonpolar end to it, which we call the tail. Okay, so here's an example of soap. Okay, where at one end of it, it's very ionic. This is a negative charge. It's hard to see, but this is negative. So this is very, very ionic. This is very water soluble. Okay, water soluble. But then you have this gigantic nonpolar hydrophobic tail that's very insoluble. So soap, what makes soap work? So if you think about it, imagine if you're frying up something that produces a lot of grease. All right, like sausage or bacon or something. All right, and when you try to clean the pan, you have all this oil there. Well, if you just pour water on it, it's not going to do anything. The oil just stays there. Okay, you have to somehow, right, because water is not going to mix with all that fat. So when you put soap in it, you ever think, why does soap magically make it all like all dissolve and vanish? Well, it's because soap has both a nonpolar and a polar tail to it. It takes fat and it makes it water soluble. Okay, so soap turns oils and fats and things like that water soluble, so water can wash it away. And the way it does that is this very non-polar part of it interacts with the fat or the grease, and then hanging outside of the fat and grease is our polar end to it, so water can interact with it. Okay, so this is basically what soap is. You have 8 to 10, 12, 15 carbons, tail hanging off of it with a very like polarized ionic head. All right, and this is what happens. Okay, so imagine inside of here I have oil or grease. Okay, so imagine I have grease here. All right, and what happens is this is soap. So imagine this is soap. The green end of it, so kind of looks like this. This green end to it is the ionic carboxylate side, the CO2 minus. All right, and then the tail is the hydrophobic part. So what happens is the hydrophobic part inserts itself inside of the grease because it interacts with the grease, but hanging outside is our polarized head or tails, our heads. All right, our CO2 minus are hanging out. So water can interact with this very like polarized molecule now. Okay, so in water, soap forms what's called a micelle. This structure is called a micelle, where you have all these non-polar ends all interacting with each other, and outside you have all of the polar ends or the polar heads. Okay, and it's forms what's called a spherical droplet with the ionic heads on the surface and the non-polar tails packed inside. Okay, so here's actually a better example. Here's the grease. All right, with all of the non-polar tails interacting with the grease because non-polar and non-polar, but then all the polar heads are sticking outside, which water now can interact with. Okay, so non-polar tails trap non-polar material like grease and oil. The non-polar remains on the surface, sealing off the grease and oil and washes away in the presence of water. All right, so that's basically how soap works. All right, so we are going to stop right there for 7.6, and when we come back, we'll start 7.8.